You're listening to the Cyberwire Network, powered by N2K.
Maybe that's an urgent message from your CEO, or maybe it's a deepfake trying to target your business. Doppel is the AI-native social engineering defense platform fighting back against impersonation and manipulation. As attackers use AI to make their tactics more sophisticated, Doppel uses it to fight back, from automatically dismantling cross-channel attacks to building team resilience and more. Doppel, outpacing what's next in social engineering. Learn more at doppel.com. That's DOPPEL.com.
Hi, friends. I'm recording this show a day before Artemis II's scheduled splashdown to Earth. I hope with all my heart and soul that when you are listening to this, the crew have made a safe and triumphant return to terra firma. Trying to describe the Artemis II mission up to this point honestly feels like an exercise in superlatives. How many stunning photographs of our moon and the Earth in high definition? How many firsts and notable records broken? How many beautifully human moments, like Carol Crater, for example? How many jokes about Nutella and the toilet? Well, I've been inhaling all of it, maybe not so much the toilet, but I watched the launch and the lunar flyby live with my family, and I've had the NASA Live YouTube stream going pretty much constantly everywhere I go. And in the middle of all of this excitement, the White House announced its fiscal year 2027 proposed budget for NASA during the Artemis II mission, and yeah, it's a proposed cut of nearly a quarter. Man, here we go again, folks. Congress critters on speed dial, you know the drill. In the meantime, I imagine many of you are en route or already in Colorado Springs, Colorado for this year's Space Symposium. Alas, I will not be there with you this year, but I'll be waiting for a table at the Golden Bee in spirit with you all. In the meantime, today is April 12th, 2026. I'm Maria Varmazis, and this is T-Minus. This week, as we turn our sights laser-focused on the amazing things going on in the global space industry, let's check in with a notable company based out of the UK, making huge steps in space manufacturing. And that company would be SpaceForge. Now, I've spoken with them a few times over the years as this semiconductors in space startup has grown by leaps and bounds. And in this chat, I'm speaking with Alastair McGibbon, who is the head of semiconductors at SpaceForge. Our chat really gets into the why and how of semiconductor fabrication in space, and what are the advantages of using low Earth orbit for this highly specialized manufacturing process, and how can it scale? Here's our conversation.
Okay, so I'm Alastair McGibbon, and I'm head of semiconductors at SpaceForge, so I'm responsible for anything to do with the manufacturing space of semiconductors and then making the most terrestrially of the semiconductors we produce and getting those semiconductors into global supply chains.
Wonderful. Well, thank you so much for joining me today, and congratulations to you and everyone at SpaceForge. The whole reason that we're chatting today is that you all just marked a huge success with Forgestar 1 successfully generating plasma aboard. Can you tell me a bit about what does that mean and why is that so crucial in semiconductor manufacturing?
Well, what that means in terms of the materials we make, so our focus is to make the most of in-space conditions to be able to grow semiconductors, and the process that we've chosen is called plasma-enhanced CVD, so chemical vapor deposition. In fabs terrestrially, people use that process, but it's a complicated semiconductor process, and what we're trying to do is replicate that in a satellite in low Earth orbit. So that's the first thing we have to do, is if we can get a payload up with the basics of that semiconductor process. So the ability to store gas, manage gas around the system, fire up a plasma so that when you put gas into the plasma, the gases will break down and you can start to be able to grow the material you want to grow.
Mm-hmm.
So what we've got on orbit are all those elements to be able to do that. So we've proven that we can actually get a semiconductor tool in low Earth orbit. The next thing is to go for a scale up where we can start to grow material of a scale that we can prove basically that crystals grow better in space. So that's where we are.
Wonderful. Well, I'm very curious about the genesis of the whole idea here. Given your expertise in semiconductors, I'm curious. I mean, for a long time, was it sort of known or maybe dreamt of that space could be an ideal environment for this kind of crystal growth, or was it just let's try it and see what happens?
Yeah, well, there's a lot of data going back to the 70s that your crystal growth is better in some form when you're trying to grow materials in low Earth orbit. So even back to Starlab in the 70s, there was the Wake Shield project, which showed you can start to grow semiconductors. And NASA have done a study of over 100 cases where, the general truth is that crystals grow better. That could be the homogeneity or the growth rate or the quality of the crystals, where you can get 2, 3, 4 orders of magnitude lower defectivity, so better quality. So the founders of SpaceForge identified that as an opportunity. Obviously, that's a long way from actually being able to manufacture semiconductors reliably, which is where I've come in terms of how do we make the most of a payload tool to really optimize in space conditions so that what we grow is going to be reliably better than anything that can be done on Earth. And that's all the steps we're taking at the moment. But we're standing on the shoulders of giants in that there's been a lot of data that shows it's better, but we're now focusing on, well, how do you actually make money out of that?
Yeah, that's always an important question, especially in the commercial field. Makes a lot of sense. Yeah, when I was reading the press release, a phrase that really stood out to me was that this plasma was called a space-grown seed. Very evocative phrase there, and I'm curious. Getting that back to Earth obviously is a challenge in and of itself. Are there concerns about? Is there fragility with what has been grown in space? Are there concerns there? Can you tell me a bit about sort of what happens after the plasma is generated?
Yeah. So the CVD process, chemical vapor deposition, what you do is you grow basically circular wafers, and then if you keep growing on top of that, you effectively grow an ingot, which is circular of a crystal. So most semiconductor crystals are grown that way, or in the case of silicon, it's a seed in a melt. But when we talk about a seed here, we're talking about a seed wafer. So initially for the materials, it's just literally a 1 or 2 inch diameter material, which we'd eventually want to make bigger as we get at that. So what you do on orbit is then grow a seed wafer on a substrate, and that substrate is on quite a rigid block, actually. So we've done plenty of sort of experiments and analysis to show that that's not a problem. You bring all that back, it can survive. And in fact, we're also doing missions with some other partners where we're just proving that, we're getting more data to prove that that's okay. So when we talk about a seed wafer, we can literally be talking about material that's only a few hundred microns thick. The importance is the quality of that material.
Yeah.
Because when you grow in a seed in semiconductors, generally the quality of the ingot is only as good as the seed you start with. Right? And that's the main premise. So you basically almost do in space what space can only do. You focus in on the value-added piece of really high-quality crystal material, of crystals that are harder to grow. And then when you bring them back, you can use terrestrial processes to grow on these crystals and scale them up. And that way you're starting to see how you can get a business case from that, because you're just focusing, obviously space is still very expensive, even though the cost of launch is going down. You basically split it. So you're doing the high value added piece in space and then scaling up terrestrially. And that means we also have to be effectively a very good semiconductor company when we're doing growth on Earth, on our space seeds. And we're doing that as well. We're developing our space capability, but we're also developing our terrestrial growth capability for the market.
We'll be right back.
This episode is brought to you by Indeed. Stop waiting around for the perfect candidate. Instead, use Indeed sponsored jobs to find the right people with the right skills fast. It's a simple way to make sure your listing is the first candidates see. According to Indeed data, sponsored jobs have 4 times more applicants than non-sponsored jobs. So go build your dream team today with Indeed. Get a $75 sponsored job credit at Indeed.com/podcast. Terms and conditions apply.
K-pop Demon Hunters Haja Boys Breakfast Meal and Huntrix Meal have just dropped at McDonald's. They're calling this a battle for the fans. What do you say to that, Rumi?
It's not a battle. So glad the Saja Boys could take breakfast and give our meal the rest of the day.
It is an honor to share.
No, it's our honor.
It is our larger honor.
No, really. Stop.
You can really feel the respect in this battle. Pick a meal to pick a side.
Ba-da-ba-ba-ba.
At participating McDonald's while supplies last.
Oh, okay. So I think that's a great segue into a question I'm sure you hear a lot about. What kinds of semiconductors, what are the applications that are especially prime for this kind of manufacturing process? Are there certain types, or is it rather globally ideal?
Well, no, it's definitely certain types initially. So what we're not doing is silicon. So silicon is a highly mature, multi-trillion-dollar industry where you have very high quality materials. Our focus is on the sort of non-silicon materials, which can be much harder to grow. And there are markets where these materials are starting to penetrate into global markets, but the problem is they're very limited by the quality of the material and how far they can go. So the types of materials we're focusing on are called wide and ultra-wide bandgap semiconductors. So that can be silicon carbide, gallium nitride, diamond, or next generation materials like aluminum nitride. And these materials, they're limited. What you use them for is for high voltage applications or energy applications where these materials can take a much higher voltage across them than silicon can. So for example, silicon carbide is used in Teslas in the power management system because you can get 1,200-1,500 volts across a silicon carbide device, whereas silicon's only about 100 or 200, right? But the problem is the quality of the material has lots of defects in it, so the yield is very low. And if you can theoretically go to much, much higher voltages than just 1,000 or 2,000, you can go to 10,000 or 20,000, but you're limited by the quality of the material. It will just break down if it's not a perfect crystal. And then the other aspect is, diamond is an important material for that sort of thing, but also, quantum computing and sensing. That requires very, very high quality crystals and the ability to control the dopants within that. So what they have is some vacancy centers of elements that aren't the base material, which you can then control to turn into quantum computers.
Oh, wow.
So by using space manufacturing for that, you can get very high quality crystal, but also very, very good control of the dopant materials that you have within that crystal. So you're opening up markets in high voltage technologies like power electronics or RF for transport and energy. But then you're also opening up the quantum markets as well, potentially within space manufacturing.
And I could see further down the line that there are in-space applications for all those technologies that you mentioned. And it would be fascinating to see if semiconductors manufactured in space end up being back used in space.
Yes. Yeah. Well, so our process itself, so because it's a plasma deposition, so plasma can do two things. It can help to grow material, but can also etch it away. So what you've got there then is two basic semiconductor processes. If, for example, you had some way of doing some sort of direct write process, then you've got the start of the ability to perhaps make photovoltaic cells in low Earth orbit or on the lunar surface for space use. It's very, very different from semiconductor manufacturing. The devices and materials that you're likely to make in space in the future are very unlikely to replicate what you do on Earth. It's going to be something different.
Oh, but that's got to be a fascinating challenge to.
And there's a lot of people already starting to think about that. And so, how do you actually make a viable semiconductor device in space? What you certainly can't do is sort of, fabs in space where you're almost replicating what is done terrestrially. It's got to be something different and much more value added.
That's a fascinating idea. My father used to work in a fab. I remember hearing many of his stories of days in the fab, and just imagining that.
These are, very, very complex.
Yeah.
So it's the most complex manufacturing process created by man are some of the advanced semiconductors. So they're very complex, but there's perhaps simple versions or high value added versions you can start as an initial point of developing in space manufacturing. Where you go beyond that, just take it step by step. But the important thing is to focus on the things where there's a real advantage first, develop that, and then see where that technology starts to take you.
And that's T-Minus Deep Space, brought to you by N2K Cyberwire. We'd love to know what you think of our podcast. Your feedback ensures we deliver the insights that keep you a step ahead in the rapidly changing space industry. If you like our show, please share a rating and review in your podcast app, or you can send an email to space@n2k.com. We're proud that N2K Cyberwire is part of the daily routine of the most influential leaders and operators in the public and private sector, from the Fortune 500 to many of the world's preeminent intelligence and law enforcement agencies. N2K helps space and cybersecurity professionals grow, learn, and stay informed. As the nexus for discovery and connection, we bring you the people, the technology, and the ideas shaping the future of secure innovation. Learn how at n2k.com. N2K's lead producer is Liz Stokes. We're mixed by Elliot Peltzman and Trey Hester, with original music by Elliot Peltzman. Our executive producer is Jennifer Ivan. Peter Kilpie is our publisher, and I am your host, Maria Varmazis. Thank you for listening. We'll see you next week.
Hey, business owners, the NFL season is a big revenue driver. Now there's a smarter way to get ready. EverPass is the only authorized commercial platform for NFL Sunday Ticket, delivering every live out-of-market regular season Sunday afternoon game. Lock in the best offer now with up to 40% off, saving up to $2,500. For the first time, you can pay over 9 months. Get up to 6 free devices and a free bar kit. Sign up by April 27th. Visit everpass.com. Limited time offer. Terms apply.